Now that we have the self-attention operation defined, we can start building it into a full model. Such models are called transformers. It's not precisely defined what makes a transformer, but we'll stick with the definition that a transformer is a sequence model where the only or primary operation that propagates information along the time dimension is self-attention. There may be other operations, but these only look at each token by itself, without taking into account what happens elsewhere in the sequence. The idea of transformers started in the domain of sequential data, but it has been extended to other domains as well. In this section, we will discuss the main things we need to add around the self-attention operation in order to create a full-fledged transformer. Along the way, we will show some of the more famous models that have been introduced over the years. The main idea that will turn a self-attention layer into a transformer is just to stack a large number of self-attention layers together into one big model. However, to make this work well, we need a few additional ingredients. Here are the main ones: the feed-forward layer, the layer normalization, and residual connections. The first addition is that we will add some feed-forward layers. We've seen these already in the sequences lecture, as a simple example of a sequence-to-sequence layer. The idea is that they apply the same MLP, or feed-forward network, to each input vector individually. This doesn't allow information to propagate between the different positions in the sequence, but it does allow some nonlinear processing of the individual tokens. The way this is usually set up is that a single feed-forward consists of two fully connected layers, where the first projects up to a hidden size of 4 times the input size, followed by a ReLU activation or a similar nonlinearity, after which we project down again to the input size with no nonlinearity. Next up is layer normalization. We've seen already that it's important in neural networks to normalize your input and to choose your initialization carefully. The idea is that the magnitudes of the hidden values at each layer should remain roughly the same, not blowing up or shrinking down to 0, and so should the gradients propagating back down the network. In deep networks, careful initialization and normalization is not enough. If you go deep enough, you'll always see some amount of vanishing gradients. To combat this, we can simply put a normalization step halfway up our network. This is no different from the computation that we used to do the normalization, or standardization as we called it there, on the initial data. The only difference here is that we perform this computation on the intermediate values of the network. We just compute their mean and standard deviation, and then subtract the mean and divide by the standard deviation. Since this computation is entirely differentiable, we can make it part of the neural network and back-propagate through it. We use operations, summing and dividing, for which the gradients are well defined, so we can just work the normalization into our computation graph. Here's what that looks like as a sequence-to-sequence operation. We get different kinds of normalization layers depending on what we normalize. For instance, if we normalize a tensor of intermediate values so that along the batch dimension the values are mean-centered with variance 1, we call that batch normalization. In layer normalization, as it is used in transformers, we apply the normalization internally to each vector. That is, we compute the mean and standard deviation of all the values within vector x3, and then use these to normalize only the values within that vector to create output vector y3. To give the algorithm step by step, for a given vector x, we compute the mean mu and standard deviation sigma over the values of that vector. We then subtract mu from each element of x and divide by sigma. The result, y, is a linearly scaled version of x, whose values are mean-centered and have variance 1. Finally, we can optionally multiply the output vector y3 by a vector of weights w and a vector of biases b. The values of these we learn. This allows the output to be no longer mean-centered or have variance 1. The idea is that we can have our cake and eat it too. The output can have any mean and variance, but internally it's first normalized. Because of the normalization, we get good propagation of gradients, and because of the rescaling step, we get any scale and mean of output we like. Since this final step is purely linear, it doesn't harm our gradients. Another cheap trick to help your gradients propagate, especially during early training, is to simply add a connection around a block of layers. We take the input of the block and add it to the output, sometimes multiplied by a single scalar parameter, but that usually isn't necessary. This is called a residual connection, and the only requirement is that the input has the same shape and size as the output. The benefit of the residual connection is that at the start of training, when the gradient signal through the block is weak because of the limits of initialization, there is a second signal through the residual connection that doesn't suffer this decay. The lower layers can then start training based on this signal, and later when the layers within the block start to do something useful, integrate the gradient that propagates through the block. With this, we can define the basic building block of transformer models, the transformer block, sometimes called a layer, but that term is a little overloaded. The details differ per transformer, but the basic ingredients are usually self-attention, a feed-forward layer applied individually to each token in the sequence, a layer normalization before the self-attention and before the feed-forward, and residual connections around the self-attention and around the feed-forward. On the left is what such a block looks like implemented in PyTorch. With our transformer block defined, we can now start building transformers. Here is a very simple example. A classifier to predict whether a given one-sentence restaurant review is positive or negative about the restaurant. This task is called sentiment classification. The input is a sentence broken up into words. We map these words to embedding vectors, as shown in the sequences lecture. And then this sequence of vectors is fed through a stack of transformer blocks, with the output of one transformer block becoming the input of the next transformer block, resulting finally in a sequence of output vectors. To reduce this to one vector that represents the whole sequence, we average over the time dimension. We then use a single linear layer to project this down to two output nodes, one for each of our classes. We apply a softmax to give us class probabilities, and we use a log loss to train the whole network. This should give us reasonable performance, but this model still has a few limitations. To start with, we haven't yet dealt with the fact that the model doesn't have access to the positions of the words. Here are two sentences with exactly opposite sentiments. However, they contain exactly the same words, just in a different order. That means that in our model, the embedding vectors going in will be the same, just in a different order. And since the transformer block is permutation equivariant, the outputs will also be the same, but shuffled. The problem is that we then average the vectors, and the shuffling won't affect the average. In short, our model will assign these two sentences the same label, whatever the value of its weights. This is what we mean when we say that the self-attention is fundamentally a set operation. It treats the input as a set, and it cannot look at the ordering of the tokens. If we want the model to pay attention to the way the tokens are ordered, we need to tell it how they are ordered in the first place. Position embeddings are one way of achieving this. The idea behind position embeddings is simple. Just like we assign each word in our vocabulary an embedding vector, which is always the same regardless of where the word appears, we also assign each position in the sentence an embedding vector, which is always the same regardless of which word appears at that position. For each token in our input, we then simply add together its word embedding and its position embedding. This way, the input for the first the in the input sequence and the second the are different, because the first is added to the position embedding for position 1, and the second is added to the position embedding for position 4. This breaks our equivariance. The position embedding becomes part of our embedding vectors and is fed to the self-attention. The model can now see at which position in the sentence each word occurs. This is very effective and very easy to implement. The only drawback is that we can't run the model very well on sequences that are longer than the largest position embedding observed during training. There are a few alternative approaches that solve this problem to some extent. Next, we need to think a little bit harder about what we feed the network with. What will be the constituent parts of the input sentence? What does one input vector correspond to? We call these the tokens of our data. We've seen already that we can break a chunk of natural language into either characters or words. If we break our sequence into words, we will have to deal with a very large vocabulary. That means a large output layer if we're doing next word prediction. It also means that we can't really deal well with things like typos, noise, or bits of text that are written in another language. Even if we set the vocabulary to 1,000,000 words, we will still encounter words that we cannot feed to the model. An alternative is to break the text up into a sequence of characters. The upside here is that we can deal with any word we encounter, even if it's spelled incorrectly. The downside is that we get a very long sequence. Note that in self-attention, the matrix of attention weights we compute is of size L times L, with L being the length of the sequence. That means that as the sequence length grows, our computation grows quadratically with it. Put simply, long sequences are the main bottleneck for transformers. So the more data we can cram into a given number of tokens, the better. The middle ground between these two options is subword tokenization. We learn a vocabulary of short character strings that are common in the data. These could be words, but also parts of words or individual characters. Then, when we process a piece of text, we break it up into character chunks that are in our vocabulary. We try to do this in such a way that the text is fully represented in as few chunks as possible. And these chunks then become our tokens. For example, let's assume that we have a vocabulary containing all lowercase letters, all uppercase letters, and all common punctuation marks, as well as these multi-character chunks shown in blue. We are then given the input "the man commands the plan" and asked to break it up into chunks that occur in our vocabulary. This means that we can represent the word man in the sentence in 3 tokens using the 3 single character tokens MAN, but this is not the most efficient way. For example, we have a multi-character chunk an in our vocabulary, so we can also represent it as M followed by an in 2 tokens. And in fact, we have a 3-character token man in our vocabulary, so we can represent the whole word man as a single token. This uses the fewest tokens, so it's the preferred approach. For plan, the whole word is not in the vocabulary, so we are forced to represent it in 3 tokens: the letter P, the letter L, and the multi-character token AN. With this approach, we have the best of both worlds. We can create a vocabulary with as many subword chunks as we can handle computationally. A common amount is about 50,000 to 100,000, which means that we can have as many common words in the vocabulary as single tokens. If a sentence is very regular and properly spelled, we'll tokenize it in about the same number of tokens we would get if we used word-level tokenization. If there are typos or uncommon words, we will need to revert back to single-letter tokens. We'll get a longer sequence, but at least we can still represent everything in the sequence and feed it to the model without loss of information. So, how do we decide what our vocabulary should be? The most common approach is to look at our training data, to start with a character-level tokenization, and to then merge pairs of tokens recursively. For example, we first merge the character bigram AN, and then we retokenize the sequence with this addition to our vocabulary. We then repeat the process. Note that when we do this, the old token AN stays in the vocabulary. It's possible that in future steps, 2 multi-character tokens get merged into an even larger token. For example, we can merge the tokens M and AN into the token man. Note that when we do this, the old token AN stays in the vocabulary. In the word plan, it's still used. While in the words man and commands, we now use the new 3-character token. There are a few approaches for deciding how this should be done in detail, specifically for how we should choose the next pair of tokens to merge. Byte pair and word piece tokenization are probably the most popular algorithms. In practice, it seems the differences don't matter all that much. And with that, we have all the ingredients to describe our first real-world transformer model, BERT. The name stands for bidirectional encoder representations from transformers. It followed the model Elmo and started a brief trend of naming language models after Muppets. BERT consists of a single stack of 24 transformer blocks. Its input, hidden, and output vectors have 1024 dimensions. The self-attention has 16 heads and the context length is 512 tokens. The idea of BERT was to pre-train the model on a large amount of text in an unsupervised way, and then to fine-tune the model on labeled data. For pre-training, we are looking for tasks that first don't require any labels, and second, are likely to lead the model to learn representations that capture a lot of structure and meaning of the text. The idea is that if we don't need labels, we are free to train on a huge amount of high-quality language data. This is easy enough to find on the internet, so we are limited only by how much data we can expose the model to within our computational budget. BERT used two tasks for pre-training. The first and most important one is masked language modeling, or MLM. For this task, we project the model's 1024-dimensional output up to a V-dimensional output, where V is the size of our vocabulary. We then softmax this output so that at each position in the sequence, the model predicts a token in our vocabulary. We then corrupt 15% of the tokens in the input sequence. The model's task is to predict what was originally in place of the corrupted tokens. The loss is a simple log loss on the correct answer, which we know since we did the corrupting in the first place. The loss is only computed on those tokens that we corrupted. We corrupt tokens in one of three ways. For 80% of the corrupted tokens, we replace the original token with a special token called a masking token used only for this purpose. For the rest, we replace the original token with a randomly chosen token from the vocabulary. For a small proportion of these, we leave the original token but still treat it as a corrupted token. That is, we still compute a loss on this position. This last trick ensures that the model doesn't focus only on the tokens that it knows are corrupted. We want the models to produce good embeddings for every single token in the input sequence. The idea behind masked language modeling, just like next word prediction, is that doing this task well requires us to understand the structure and some of the meaning of the sentence. If we train a model to be good at masked language modeling, it's likely that the representations it produces, before we project them to tokens, capture a lot of the structure and meaning of the sentence. The BERT authors wanted to test BERT on two types of downstream tasks after the pre-training phase. Some that had a label for every token in the sentence, like part of speech tagging, but also some that had a label for every sentence, like sentiment classification. To ensure that at least one token could represent the sentence as a whole, they pre-trained BERT on an additional sentence-level task explicitly. For this purpose, each sequence is started with a special token written as CLS in the diagram. For the sequence classification task, we look only at the corresponding output token and discard the rest. The token is projected down to a binary classification. We then feed the model with either one sequence of 512 tokens taken from a random position in the data, called as case A, or with two sequences of 256 tokens from two different parts of the corpus, concatenated together, call that case B. In both cases, a special token, written as SEP, indicates the halfway point. The model's job now is to predict whether the two halves of the input sequence were next to each other in the corpus, case A, or not, case B. The idea is that this forces the model to look at the sentence as a whole and to represent the whole sentence and its meaning in the output corresponding to the CLS token. In subsequent research, it was found that this already happens when you train with only the MLM task, and the classification task doesn't add much. For that reason, later versions of BERT often dispense with this task. The pre-training was done on a corpus, a natural language dataset, containing text from Wikipedia and from free self-published books. This ensured that all language was carefully written and contained a reasonable mix of styles, at least encyclopedic. The data was tokenized with the WordPiece tokenizer and fed to the model in chunks of 512 tokens. For the benefit of fast training, the authors just cut chunks of 512 tokens from random positions at the corpus, not worrying about things like sentence boundaries. Interestingly, the book's corpus shows an early instance of using copyrighted content to train machine learning models, which has now become quite controversial. The book's corpus was originally described as copyright-free books by unpublished authors. But the truth is that while these books were free to read, they were not copyright-free at all. and they were used without the author's consent. Whether such consent is necessary or allowing people to view content immediately implies that they are also allowed to train machine learning models on it is a hotly debated question currently being worked out in many court cases. After pre-training, we fine-tune unlabeled data. This table is from the paper that presented BERT. Each column represents a natural language task with its own labeled training data and test data. For example, in MNLI, you are given two sentences, a premise and a hypothesis, and the task is to predict whether the hypothesis follows from the premise. This is a sequence-level classification task. We predict one label for a full sequence of text. As you can see, BERT showed great improvement across the board. In the previous lecture on sequential data, we saw that simply predicting the next token in a sequence is a great way to train a model. We call this auto-regressive modeling. If you want to do auto-regressive modeling, plain transformer blocks won't work. The self-attention operation can just look ahead in the sequence to predict what the next token will be. We will never learn to predict the future from the past. This was not a problem with LSTMs because by definition any RNN can only look back in the sequence. They are causal. But, like convolutions, self-attention need to be made causal in order to be used in autoregressive settings. The solution is simple. When computing the third output, we simply apply the self-attention operation only over the first three elements. Anything further in the sequence than the element we're currently predicting for is ignored. Note that we apply the softmax only over these weights. The rest of the inputs should get weight 0, and the weights up to the current position always sum to 1. We call this a causal self-attention. Here is what that looks like vectorized. Note that we compute all weights and then mask out the ones we don't want. These we set to negative infinity so that they become 0 after the softmax. Since the self-attention is the only part of the transformer block that propagates information across the time dimension, making that part causal makes the whole block causal. A transformer block with a causal self-attention is called a causal transformer block. Now, a stack of transformer blocks can be put to work on the task of autoregressive modeling. The input is a sequence of tokens, and the output is projected to the vocabulary as it was in the BERT model. Then, the targets for the prediction are just the input sequence shifted one token to the left. That is, for each point in the sequence we predict in parallel what the next token will be. Like the masked language modeling, this is a great pre-training task. You can do it with only unlabeled data, and doing it well requires a lot of insight into what is happening in the part of the sentence you get to see. The GPT family of models are built this way. They are a stack of causal transformer blocks, which are trained to do next token prediction. You could see the first GPT already a few slides ago as one of the models that BERT soundly thrashed. We'll skip that one, and we'll go straight to GPT-2, introduced in 2009. One innovation in GPT-2 was that training data should be high quality. We can easily get terabytes of text from the internet, but not all of it will be very high quality writing. It turns out that filtering quality can be very important in training large language models. To collect a dataset of high quality writing, the authors looked to social media. They collected only links that received a certain number of upvotes on the social media platform Reddit. Note that this doesn't mean that the model was trained on Reddit data. It was trained on generic articles published on the web, but the articles were filtered by how many upvotes they received. The reason that we highlight GPT-2 in particular is that it represented a watershed in natural language generation. Like any autoregressive model, we can sample from it to produce some natural-looking text from a given seed or prompt. We've seen already that LSTMs can be used to generate language that is stylistically quite realistic. However, the place where they always fell down was in long-term coherence. For instance, they could generate realistic-looking Shakespeare, but the character names would never stay the same from one paragraph to the next. GPT-2, a model of quite modest size by today's standards, was the first model that showed the ability to generate long passages of text with an internally coherent structure. Here, for instance, GPT-2 continues the prompt shown in italics. The resulting news article is not only quite realistic, but it also keeps returning to the theme of the piece. The subject of unicorns keeps coming back, and it invents a Bolivian researcher with a Spanish-sounding name, remembers this name, and then refers back to it in a consistent but varied manner. This is when the mainstream media began to take note of the capabilities of modern machine learning systems, and the threats that they could represent. For OpenAI, the lab that developed GPT-2, this performance was reason enough not to release the model immediately, for fear that it could create a flood of realistic-looking misinformation. About a year and a half later, OpenAI showed off GPT-3. The architecture hadn't changed much from GPT-2, but they had massively scaled it up. The number of parameters in the model had grown from 1.5 billion, 175 billion. The model was still pre-trained purely by autoregressive language modeling, but this time on a dataset of around 800 gigabytes of text. To find this much high-quality text on the web, OpenAI took their previously relatively small set of high-quality articles and trained a classifier to predict whether an article came from this subset or from a larger unfiltered web crawl. Then they used this classifier to select high-quality data from the general crawl. This is a graph from the paper of GPT-3. Just the final training run of GPT-3 alone is estimated to have cost around $5 to $10 million in compute. It's important to note that this is not just an exercise in building bigger models for the sake of it, although it sometimes seems that way. Transformer models seem to be subject to a kind of emergent behavior that only appears at very large scales. That is, we can build models that can do stuff we never could before, but it only happens at the scale of billions of parameters and tens to hundreds of gigabytes of data. So far, we don't seem to have found the ceiling to this effect yet. The next biggest model, if we can build it, may show us yet more impressive behavior. This is leading to a lot of excitement and a kind of race to the top among big industry labs. The results can indeed be impressive, but in all this, the questions of social impact become more pronounced as well. With such massive datasets, it's hard to control what ends up in the data, which people are represented and how. The larger the model is, the less transparent it becomes, and the more difficult it is to oversee the consequences of putting it blindly into a production system. As a pre-trained model, GPT-3 was far too large to fine-tune. The idea of BERT, that a company like Google could pre-train a neural network which everybody could then download and fine-tune for their own purposes, didn't work here anymore. GPT-3 was too large even to fine-tune without $1 million cluster and a lot of complex multiprocessing. Happily, a new ability came along just in time, the ability for in-context learning. It turned out that GPT-3 was very good at recognizing patterns in its input and continuing them in a natural way. This means that you could set up some examples of a learning problem, an instance followed by its label, and then another instance, the label for that instance, and so on. Then you show the instance you actually want a prediction for, and from there on you let GPT-3 predict the rest of the sequence. If GPT-3 is successful, it will first of all continue the pattern and predict a class label in that position. Then, if it's really good, it will also predict the correct class label. It doesn't really matter how you choose to represent your data, so long as there is some pattern to it. GPT-3 will pick up on the pattern and continue it. In this way, we can use GPT-3 to do machine learning without any fine-tuning. We never do any backpropagation ourselves or make any changes to the weights. In fact, we don't even need to know the weights. All we need to be able to do is to give the model a prompt and to have it generate a continuation. We put the examples we have in the seed and we see what continuation GPT-3 predicts. For OpenAI, this was a remarkably lucky discovery. Not only did they get a new mode of learning just as the model was growing too big to fine-tune, but also in-context learning is much easier to commercialize. You don't have to give people your model and let them fine-tune it. You can just offer an API that will let them run GPT-3 on a prompt of their choice. Here is an example of a more complex in-context learning task from the paper that introduced GPT-3. The aim is to use an invented word in a sentence, given a one-sentence definition. The first definition and sentence pair in gray is given in the prompt. Both are written by a human being. A huatpu is a small furry animal native to Tanzania. An example of a sentence that uses the word huatpu is, "We were traveling in Africa and we saw these very cute huatpus." Next, a second definition is given. To do a fardaddle means to jump up and down really fast. An example of a sentence that uses the word fardaddle is, at this point, we stop the prompt and we ask GPT to continue it. Its continuation is given in black. One day when I was playing tag with my little sister, she got really excited and she started doing these crazy fardaddles. This continuation is appended to the prompt. We add a new definition and we ask ChatGPT for a continuation of the entire prompt, including its earlier answer. This, incidentally, provides a hint of GPT's future. This way of alternating human input and text generated by the model is not a million miles away from a chat between the model and a human user. This is the basic idea behind most transformer models. The simplicity and homogeneity compared to models based on LSTMs are a great benefit of the model family. This means transformer models are easy to scale up to huge numbers of parameters. Most claims you will see of models with hundreds of billions of parameters being trained refer to transformer models. Finally, one point to keep in mind as you dig into the literature. If you read other descriptions of transformer models, you may quickly run into the words encoder and decoder. In fact, most tutorials I can find seem to start there. The first thing to know about transformers is that they consist of an encoder and a decoder. This is decidedly not true. At least not if you consider BERT and GPT transformers. Neither of these have an encoder or a decoder. They are just simple stacks of transformer blocks, nothing more. In fact, there is really only one transformer model worth mentioning here that has an encoder and a decoder component. And that is the original transformer. The model that first showed that with just self-attention, you could get state-of-the-art performance. Attention had existed for a long time as a way to boost the performance of recurrent neural networks. But this paper, appropriately titled "Attention is All You Need," showed that if you remove the RNNs and beef up the number of attention operations, you get a much more parallelizable model that still shows state-of-the-art performance. Now, this model was a little bit more complex in its architecture than the BERTs and GPTs that came after. Specifically, it consisted of two parallel stacks of transformer blocks, one functioning as an encoder and one as a decoder. The reason for this was simple. The original transformer was not trained for unsupervised language modeling, but for machine translation. It was given one sentence in language A, and it was supposed to translate it to language B. There was no pre-training here. That only came with GPT and BERT. The whole model was trained on labeled data, that is, pairs of sentences. For this reason, it made sense to train one half of the model to read and represent the input sentence in language A, and another half of the model to generate the predicted sentence in language B. But it's important to note that this whole encoder-decoder business is just a consequence of the task of translation. It has nothing to do with the tasks that transformers were put to later, and almost all models that came after simplified the idea to a single stack of transformer blocks. The encoder-decoder idea still has merit in some settings. However, it's important to note that it's not a fundamental part of what makes a transformer a transformer. If you use it, you should know why. All this was the basis for the ChatGPT system that has caused such upheaval in recent years. But GPT by itself isn't a chatbot yet. In the final part of this lecture, we'll look at what's necessary to turn a next token predictor into a well-behaved chatbot.